Good afternoon, class. In today's video, what I'd like to do is to go over collisions. So this video will be in two parts. The first part will be on elastic collisions, and the other one will be on inelastic collisions. And like I said in other videos, I recognize that I'm saying elastic collisions a little bit weird, and the reason for that is so that when I say inelastic collisions, there's a clear difference between the elastic and inelastic versus the elastic and inelastic. So just to hear that difference. Okay, so in this example, we've got two cars, and they're going to be two different problems given based on the different colors that I've been using. So we've got car A traveling with a momentum P1, and we've got car B, and there's two examples. The first one is it's traveling backwards towards car A with momentum P2, or it could be traveling away from car A in the same direction as car A with a momentum of P3. So in this case, what I did was I wrote down the elastic collision equation, and then so what I did from here was I gave two different examples. I drew this red line here to show that this is all of my assumptions, and then this is all of my work over here and over here. So let's start with the assumptions. I'm going to assume in this example that the P1 initial is the same as twice the P2 initial. I'm going to assume that this direction is positive. I'm also going to assume that the final momentum of car A is going to be 0 kilogram-meters per second. That is not at all true. Usually that's not the case, but we're going to make that assumption just to show the point of what happens during collisions like these. We're also going to assume that the initial momentum of the car is negative 5 kilogram-meters per second. Now, you might be asking, why negative 5 kilogram-meters per second? I understand the 5 kilogram-meters per second is just an initial condition, but why negative? And that's a good question. The answer is because P2 or car B is traveling this direction, and we established that this direction is positive. So therefore, this direction is negative based on our convention. Of course, if you flip the convention around, you could always make P2 initial positive, but you would have to make P1 initial negative in response because they are traveling in opposite directions. Okay? So with that, let's input all of our assumptions into this problem over here. So we've got 2 times P2 initial minus P2 initial, which is going to be P1 final 0. We don't know what P2 final is, so we're going to have to wait on that one. So then we plug in our numbers, and what we find is that it's going to be 2 times 5 minus 5, and so 2 times 5 is 10, minus 5 is still 5, so our final momentum is going to be 5 kilogram-meters per second. So now the whole reason why I did this was to show what is the change in momentum. Because if this car was going to hit car B and car B was not moving, that would actually change this completely. Because if the initial momentum was 0, the change in momentum would only have been 5 kilogram-meters per second, which is, depending on the length of the collision time of the collision, it might be survivable. But this is because they're coming at each other in a head-on collision, that change in momentum is now twice as big because of that head-on collision. So, and the reason why is because the change in momentum is P2 final minus P1 final. And if P2 initial is negative, then negative times a negative is a positive. So you're going to add them together. So that's just to keep in mind. Anytime that you have collisions like this, they can be very bad, and they can get really bad really quickly. Which is also why, if you've ever noticed in bumper cars, you've never seen bumper cars move very fast, and yet every time people get hit or when there's a collision in a bumper car scenario, everyone gets jerked around quite a bit. And the whole reason for that is and that's why they keep their speeds very low, because these elastic collisions can make these changes in momentum quite big. And more than you would even expect, which could lead to injuries if you don't keep the speed itself very low. So now let's go into the other scenario. What if the car is moving away from, what if car B is moving away from car A at 5 kilogram meters per second? Would that change everything? A little bit. But we're going to make a few very general assumptions. Again, assumptions that are probably not all that realistic, but that's okay. We're going to have to just deal with it in terms of to keep everything simple. So those assumptions are, we're going to allow that P1 initial is going to be the same as the last time, which is twice P2 initials value. We're going to again allow this direction to be positive. We're going to assume that P1 final is 0 kilogram meters per second. Again, that's not going to be how that's not a good assumption necessarily. It's not a realistic assumption. There's always going to be some kind of collision where there's like these two cars will probably bounce off of each other. So that's in real life that doesn't work, but for just to get the idea of what's happening, that we're going to make this assumption for simplicity's sake. We're also going to assume that P2 initial has the exact same momentum that it started with over here. The only difference is that because it's moving this way, it's going to be positive 5 kilogram meters per second instead of negative 5 kilogram meters per second. So given all that, let's turn to our green chart and our green problem, where it's the same. It's all of this is the same, except that there's a plus sign here instead of a minus sign, and that's important because then now the change in car 2 is going to be the final momentum is going to be 15 kilogram meters per second, and the change in momentum is still 10 kilogram meters per second. Now, that's where I have to do a little bit of commentary, because it seems like in both of these scenarios that the change in momentum is the same, so it's still going to be just as damaging. And to be fair, if these assumptions are correct, then yes, the change in momentum is the same in both scenarios. It'll be just as damaging whether you're going away from the car or coming towards the car. But that's not always the case. And of course, this is only talking about the collision between car A and car B. It is not talking about the damage being done with you in the car. If you are in that car, that's a whole different story, because it's a whole nother set of collision equations that we have to take into account. For example, I've assumed in this case that both of these cars are the same mass. You are not the same mass as those cars. So even though your car collides with, let's say you're in car A and you collide with car B, when it comes to how well you take the impact, there are many factors here that actually do matter. One of them is the fact that let's say take my mass, for example, 100 kilograms. Again, that's my assumption. Even if these are even 1,000 kilograms each, which is about a reasonable estimate for a car, this impact is going to be 10 times harder on you. So what could be a possibly survivable collision if you were the same mass as the other person colliding into you now becomes extremely deadly. So it's one of those things that's why we build all of these safety features. In fact, the whole reason that this green set of assumptions would be more survivable for a person in car B going this way is because there's a seat that is cushioned to take some of that impact away from them. Whereas if the two cars are heading towards each other and having a head-on collision like that, unless there's a airbag, there's no, the person in car A and B are going to smash into the steering wheel, which is very hard last I checked. So that's one thing I want you to think about. Even though we've got two different sets of problems that look relatively the same, they actually and they calculate out the same. So you might think, oh, they're the same scenario. There's actually a whole lot more going on to them, but because these assumptions are not going to be always that simple. However, if you can make your assumptions correct, you can get your answers will be a little bit, not only a little bit different, but it will be a little bit more realistic. So One thing that I want to make sure you understand, there's a balance between how easy a problem is in terms of, or how simple a problem is, and how realistic a problem is. This is a good example of that, where you would have most of us have an instinct that if you have a head-on collision, chances of surviving are very low. If you have a collision where it's a rear end collision, the chances of surviving are very high. And so that's just to give you an idea that you have to make sure your assumptions are always correct. Otherwise, you can get some answers that, even though mathematically I did everything correct, they may not come out to what you would instinctually say because of your experiences in real life. So that concludes the elastic collisions. What I'll do next time is I'll go over inelastic collisions. So good luck in your studies, and may the force be with you.